So you've probably used a GPS to get from your house to a new pizza place. You punch in the address and boom, it spits out the fastest route. But have you ever stopped to think about what's happening behind the screen? How does your phone know that taking Main Street is 5 minutes faster than slogging through downtown traffic? This isn't just magic. It's the brilliant work of algorithms. These are like super detailed recipes that computers follow to solve problems. And one of the most fundamental problems they tackle is finding the shortest path between 2 points. It's a puzzle that shows up everywhere, from your daily commute to the internet itself. For a delivery company, it's about saving fuel and time, which means saving money. For the internet, it's about sending your data packet across a massive network of cables and routers. If these systems chose a bad path, your pizza would be cold, your package would be late, and your video would buffer forever. All right, let's talk about one specific hero in this story, the Bellman-Ford algorithm. Imagine you have a map, but this map is a bit weird. Some roads might actually give you something instead of costing you time. Think of it like a road with a special toll booth that pays you to drive on it. This is where many simpler algorithms would get totally confused. They can't handle these negative costs, or what we call negative weights in computer science. This is precisely where the Bellman-Ford algorithm shines. It was developed back in the 1950s by Richard Bellman and Lester Ford Jr. Let's make this real. Imagine you're running a small food delivery service. Your kitchen is at point A. You have deliveries to make at point B, point C, and point D. You want to figure out the cheapest route from your kitchen to each of these delivery locations. We start by assuming the worst. The cost to get from our kitchen point A to itself is 0, obviously. But for every other location, we'll start by saying the cost is infinity. This sounds dramatic, but it just means we haven't found a path to them yet. We're standing at the kitchen, completely clueless about how to get anywhere else. Now, we begin the first round of updates. Let's say there's a road from A to B that costs $10. Since our current cost to get to A is 0, the cost to reach B through A is $10. Is $10 better than infinity? Absolutely. So we update the cost for B to $10. We do this for every road. Now, let's add a tricky road, a path from C to B that has a cost of -6. This is one of those money-saving shortcuts. The cost to get to C is 15. The cost of the road from C to B is -6. So, the new potential cost for B is 9. Hey, that's cheaper than our current best cost for B, which is 10. So where does our trusty Bellman-Ford algorithm flex its muscles in the real world? Its biggest stage is in network routing protocols. The internet is a gigantic, sprawling network of routers. Data packets need to be sent from source to destination as quickly as possible. Bellman-Ford's ability to handle complexities and detect instability makes it foundational in this field. Think about financial systems. Arbitrage is the practice of exploiting price differences in different markets. You could model this as a graph where currencies are nodes and exchange rates are paths. A series of exchanges that results in a profit is a negative cost cycle. Bellman-Ford is perfectly suited to detect these arbitrage opportunities. From ensuring your email gets delivered efficiently to powering complex logistics and financial analysis, this nearly 70-year-old algorithm remains a quiet but powerful force. It's a true superhero, working behind the scenes to solve some of our most challenging real-world puzzles, shaping our connected world one optimal path at a time.